Welcome to The Explainer. Today, we're cracking open a classic graduate math text, Saunders-MacLane's Categories for the Working Mathematician. We're going to dive into its 9th chapter on special limits and explore some really powerful tools mathematicians use to handle mind-bending concepts like complexity and infinity.
So how do you even begin to do that? I mean, it's a huge question. Well, the thing is, they use tools that go way beyond simple counting and shapes. They need specialized tools, ones designed to manage these enormous, interconnected systems that are always growing or flowing in a specific direction.
All right, so here's our game plan. First, we'll take a look at the standard tools and see, where they come up a bit short. Then, we're going to introduce two powerful upgrades. First, the idea of filtering, which helps us manage systems that have a clear direction, and then something called an end, which is wild. It's like a form of calculus for these abstract structures. And finally, we'll pull it all together and see why these ideas are such a game changer.
Okay, so before we jump into the really special stuff, we need to get a handle on the standard toolkit. Think about basic operations, like products, where you bundle objects together, or pullbacks, where you find their common ground. These are super fundamental ways to combine mathematical objects, but they all rely on a fixed, rigid blueprint you set up beforehand.
Exactly. What happens when you're not just snapping together a static structure, like Legos, but you're trying to describe a process that actually unfolds over time, or a system where everything is constantly moving forward and hopefully coming together? Well, your standard limits aren't always the right tool for that job.
And this is where our first special tool comes into play. To really get a grip on these directed systems, we need categories that have a very special property. They need to be what's called filtered. So this definition basically just puts into math terms this idea of always being able to move forward together. It really just boils down to two rules. First, if you pick any two objects in the system, there's always a third one downstream that they both connect to. And second, if you have two different ways to get from point A to point B, you can always go just a little bit further to a place where those two paths merge and become one. It is all about guaranteeing convergence.
So what's the upshot of all this? Well, it means the system is inherently directed. It can't just split apart or fray at the edges. Because of this guarantee of convergence, any finite arrangement of paths, no matter how tangled it looks, can always be extended to form a single unified cone that's pointing toward the future of the system.
And this image is just the perfect analogy. Think about it. The objects and arrows are like the streams in a river delta. That filtered property is the thing that guarantees that no matter which little channel you start in, they will all eventually merge and flow into the same main river. It's just a beautiful way to picture convergence. Now, this might look a little technical, but I promise you the implication is huge. A colimit is how you build a bigger object by gluing all the pieces of our directed system together. A finite limit is how you impose a fixed structure on it. What this rule says is that for sets, these two operations commute, which means the order doesn't matter. You can build first and then structure, or you can structure first and then build, and you will always get to the same place. That is an incredibly powerful guarantee to have.
Okay, so let's shift gears and look at our second special tool, which honestly is even more profound. If filtered limits are all about managing directed systems, our next concept, called the end, introduces something that feels remarkably like calculus, but for the world of categories.
And get this, the source text itself, in the notes at the end of the chapter, tells us just how fundamental this is. The idea comes from Nobuo Yoneda, one of the pioneers of the entire field, and MacLane himself stresses that this is an absolutely essential concept.
So here's the key analogy you want to hold on to. If a regular limit is kind of like summing up a bunch of separate pieces, an end is more like integrating over a continuous whole. It's a tool for accumulating information across an entire category, not just from a small fixed little diagram.
The formal definition, it gets a little deep, but the core idea is this. Instead of fitting arrows into a simple cone shape, an end uses this much more sophisticated structure called a wedge. And this wedge has to satisfy a consistency rule that respects how the system behaves both forwards and backwards. This makes it a much more dynamic, much more powerful kind of universal property, one that's capable of capturing a truly global perspective.
And the notation itself tells the story here. MacLane didn't pick the integral symbol by accident. Just like the x in the integral of f of x dx, that little c is bound. It's a placeholder. This notation is a huge clue that we're no longer looking at individual objects one by one. Instead, we are summarizing or accumulating information over all the possible choices of C across the entire category.
This comparison really gets to the heart of it. An integral finds the area under a curve by summing up an infinite number of tiny pieces, right? Well, in the same way, an n finds a single canonical object by accumulating a functor's values across an entire category, making sure the result respects all of that category's internal structure and symmetries.
And to see just how powerful this is, check out this example. Natural transformations are one of the most fundamental concepts in all of category theory. They're basically the maps between maps. And it turns out the set of all natural transformations between two functors can be calculated as a single end. This shows that ends aren't some obscure, super-specialized tool. No, they are right at the very heart of the theory.
So this comparison really sums it all up. A standard limit is a local thing. You give it a diagram, and it spits out the object that best fits that diagram's shape. An end, on the other hand, is a global construction. It looks at the entire category and asks, what is the one object that harmonizes all of the functors' internal relationships at once? It's a huge conceptual leap from a static, structural view to a much more dynamic, holistic one. Okay, so we've got filtered limits for directed systems, and we've got ends for this sort of categorical calculus. What's the big takeaway? Why does this advanced toolkit matter so much to mathematicians? Well, it all comes down to gaining incredible power and a whole new perspective. With these tools, mathematicians can finally wrestle with infinite processes that used to be totally unmanageable. They get a brand new form of calculus for abstract structures, and it may be most importantly, they start to see that all these seemingly separate mathematical ideas are really just different views of a single, deeply connected whole. And this is it. This is the most stunning insight in the whole chapter. It turns out that this special, calculus-like concept of an end is actually the more fundamental idea. Every single ordinary limit, a product, a pullback, you name it, can be expressed as a particular kind of end. The tool that we brought in to solve a special case is in fact the master key that unlocks all of them.
This idea of unification leads to one last, really provocative thought, one that Mac Lane himself raises. The book ends by pointing out that pretty much all the concepts in category theory, limits, adjoints, even functors, can be seen as instances of an even more general construction called a can extension. And it just leaves you wondering, if everything is this connected, what other deep truths are still out there, just waiting to be discovered?